Alright, now let's move on to grade 11 functions. In grade 11, you didn't learn a ton of new equations to solve, but a couple things should have come up. In grade 9, when you solved linear equations, you only got one possible answer. In grade 10, when you solved quadratics, it was possible for you to get two answers for the variable. In grade 11, you would have solved some trig equations, cosine, sine, tan, and when solving trig equations, you know those are periodic functions, like cosine is a periodic function, which means it has a pattern of y values that repeat at regular intervals. Therefore, there's an infinite number of answers for the variable x or theta, whatever you want to call it, that have the same value for y. So what happens for these types of questions is usually you'll want to find answers within a given range, and most often it'll say solve for theta between 0 and 360. So it'll look something like this. Find all answers for theta between 0 and 360. Well, we can figure out where those answers are going to be, and there's going to be two of them for cosine based on the CAST rule, C-A-S-T. Those tell us what quadrants, what ratios are positive in. Well, it turns out cosine is positive in two quadrants, quadrant 4 and quadrant 1. The quadrants are numbered 1, 2, 3, 4. Quadrant 1, quadrant 4, cosine is positive, and here's a positive ratio, so we know we will find that ratio in those two quadrants. To get your first answer, to get the answer in quadrant 1, you can either use your special triangle or just ask your calculator, what's the inverse cos of a half? When you want to solve for an unknown angle, you know the ratio, you use the inverse of cosine, and you can ask your calculator, and it'll tell us that it's 60. So inverse cos of a half is 60. So our first answer is 60, and 60 degrees is in the first quadrant, right? Here's 0, 90, 180, 270, and then back to 360. 60 degrees is about here, so there's theta 1, and the reference angle is 60. What we do is we place that same reference angle in the other quadrant where cosine is positive, reference angle of 60, and we figure out what would we have to rotate from the initial arm, the positive x-axis, to get all the way around to that terminal arm. So theta 2, well, it fell 60 short of 360 degree rotation, so 360 minus 60, theta 2 is 300 degrees. So cosine of 60 and cosine of 300, both of those values when plugged in for theta, will give us a ratio of a half. And we could have, like I said, we could have used our special triangle, right, our half equilateral triangle, 60, 30, 2, 1, root 3, and seen from this special triangle that this angle here has an adjacent over hypotenuse of a half. So that's why cos of 60 is a half. Also in grade 11, you might have looked at some exponential equations. Exponential equations are easy to solve when you can rewrite both of the powers for the same base, right? 3 to the 4 is 81, so I could rewrite 81 as 3 to the 4. And now it's easy to see that when we have something equal to each other, two powers equal to have the same base, well, that means these exponents would have to be the same thing for this equation to be true. So you just set the equations equal, and we're done. X equals 4. Well, what if you didn't know 3 to the 4 was 81? What if you couldn't figure that out? Well, when isolating a variable, I've been saying all throughout this video, you have to do inverse operations. Well, what's the inverse of an exponential function, where the variable is in the exponent? It turns out the inverse of an exponential, which you'll focus on in grade 12 math, is a logarithmic function. And the rule for logarithmic functions, log base b of x equals y, is the same thing as b to the y equals x. Here's the rule. So when you do a logarithmic function, the answer to a log, y, is the exponent you put on the base of the log to get this thing here called the argument. So log base b of x equals y, that's the same thing as saying that b to the power of y equals x. The answer to a log is the exponent you put on the base to get the argument. So I could rewrite this in logarithmic form. I'm trying to figure out what exponent do I put on 3 to get 81. So in logarithmic form, if I change this to logarithmic form using the rule, well, log base 3 of 81 equals x. This would help me solve for x. What exponent, x, do I put onto 3 to get to 81? So we can type on the calculator, log base 3 of 81. So log base 3 of 81, and I figure out it's 4, right? 3 to the power of 4 is 81. That's why log base 3 of 81 is 4. When we type this, the calculator is looking for what exponent do we put on the 3 to get the argument 81, and it turns out it's 4. Let's move on to grade 12 now. I don't think you learned many new other equations in grade 11 other than those two. So let's go on to grade 12. In grade 12, there's a few new ones. We have another exponential equation here, but more than one variable. But it's still power equals power. So I told you before, it's useful if we can rewrite those powers with the same base. And we can write 9 as a base 3 power. It's 3 squared. Now I have a power equals a power. The powers have the same base. I'm just going to do one more thing before I set the exponents equal. When you have an exponent on top of an exponent, the rule from grade 9, you learned that you multiply them. So 2 times x minus 5 is 2x minus 10. Now the only way that this equation could be true is if the exponents are the same, since the bases are already the same. So set the exponents to be equal and solve for what value of the variable makes those exponents be the same thing. Rearrange, we get 11 equals x. There's our answer. This one, I've pre-written just because it's so many steps. I'll just walk you through it quickly. It's the same as the last question, but the powers are base 6 and base 2, and it's very hard to write 6 as a base 2 power. Right? 2 squared is 4, 2 cubed is 8, so it's something between 2 and 3. Since it's not easy to write them with the same base, we use the power rule of logs and use a little trick. Take the log of both sides. Right? We can do this anything we want to in an equation as long as we do it to both sides. We take log of both sides, which then allows us to take the exponent of our power and write it as the coefficient of the log. That solves a big problem. Now the variable is out of the exponent. From there, it's just expanding to get rid of the brackets. So I expand, get that line. Then, just like in grade 9, you get all the terms with a variable. So these two have a variable on one side of the equation. I moved them to the left. Here they are here. And the other terms, this one and this one, went to the other side of the equation. Both of these terms have an x, so I common factored out the x, so I then divide both of the terms by the x I took out, and then divide this to the other side to get x all by itself, type it in, and we get an approximate answer of negative 0.97. So that's just a more difficult version of this question. When we can't write the powers with the same base, we take the log of both sides, isolate the variable that way. How about this one, a logarithmic equation? This is the first logarithmic equation we solved. So we've done exponential, but here's a logarithmic. Hopefully you remember the rule I just showed you for logs. Log base b of x equals y means the same thing as b to the y equals x, right? The answer to a log is the exponent you put on the base to get the argument. So I could rewrite this one as 5 squared equals x minus 3. Change it to exponential form. 5 squared equals x minus 3, and then that's easy enough to solve. 25, add the 3, x is 28. How about this one? More than one logarithmic expression in the equation. Well, there's a rule for that, the power rule of logs. When adding logs that have the same base, they're both base 4, we can combine them, write them as a single log with that same base, but we have to multiply the arguments together. So I combine right as a single log. Once we've done that, now this looks just like this question. A log equals a number. Once you get to log equals number, rewrite it in exponential. So 4 to the 1 equals the argument, x plus 2 times x minus 1, which I will expand. So x squared minus 1x plus 2x, that's plus 1x minus 2. Rearrange, set to 0. Right, we have a quadratic here we now have to solve. What numbers multiply to negative 6? Add to 1. That's 3 and negative 2. Use our zero product rule to figure out what values of x would make either of the factors be 0, and we get negative 3 or 2. But whenever you solve a logarithmic equation, I should have mentioned this for the last question, you have to check and make sure that your answers don't make your original equation undefined. So let's check and make sure negative 3 and 2 both work in the equation. If I plugged negative 3 in for this x, I would get log base 4 of negative 1. And there's no exponent we could put on 4 to get an answer of negative 1. Anytime the argument is negative, we say it's an extraneous root. So this doesn't actually work in the equation. But I believe 2 makes both of the arguments positive. 2 plus 2 is 4, 2 minus 1 is 1, 2 is an acceptable answer. Okay, grade 12, you'll also have to solve equations higher than degree 4. So here's a polynomial function higher than degree 2. This is a degree 4 polynomial function. What we're going to do to factor it is we actually have to just guess and check some zeros to start with to get us started. And we guess and check factors of our constant term. So factors of 12 are plus or minus 1, 2, 3, 4, 6, and 12. Those are the only values that could be zeros of this equation. If you tried 1, we would get 1 minus 2, negative 1, minus 7, negative 8, plus 8 is 0, plus 12 is 12. So 1 is not a 0. But if you plugged in negative 1, I believe it works. So negative 1 is a 0. So what we do is we are going to divide this function by x plus 1. That's the factor that would give us a 0 of negative 1. So we'll divide it by negative 1 by doing synthetic. I'll put the 0, negative 1 there, and then I'll put the coefficients, 1, negative 2, negative 7, 8, 12 there. And I bring down the first term 1, multiply negative 1 times 1 is negative 1, add those, negative 3, multiply 3, add those, negative 4, multiply to get 4, 12, negative 12, 0. There's my remainder 0, so that means that negative 1, so that means x plus 1 divides evenly into this function. Here is constant term, degree 1 term, degree 2 term, degree 3 term. So I can rewrite this polynomial in a factored form. So I divided it by x plus 1 by using the 0 of negative 1. So 0 equals x plus 1. That's what I divided by. And here's my quotient. X cubed minus 3x squared minus 4x plus 12. And then I can factor the cubic now even further. I can do that using the same method, testing zeros and then dividing using synthetic, or I'm going to notice that I could actually do by grouping here. If I common factor from the first two terms, I could take out an x squared, and I get x minus 3. Last two terms take out a negative 4, and I get x minus 3. Same type of grouping we did back in grade 10 when we were doing quadratics when a wasn't 1. So my factors here, take out the x minus 3, and I'm left with x squared minus 4, which is a difference of squares, which I'll write as x minus 2, x plus 2. Zero product rule tells me this equation would be true if any of these factors become 0. So it could be negative 1, 3, 2, or negative 2. All of those would make the equation true. All of those would make the equation equal to 0, and that's what we were trying to do. Sorry, this is my fourth answer. It was negative 2. The very last question, probably the most difficult equation you would have to solve in your high school math career, is a quadratic made up of trig equations. So I'm going to think of this, instead of cosecant squared, I'm going to think of it let's just say it's y squared for now. Let's let y equal cosecant. So I'll use a let statement. So y squared minus y minus 2 equals 0. If I was solving that, I would factor it, sum and product, multiplies to negative 2, adds to negative 1, are negative 2 and 1. So y minus 2, y plus 1 equals 0. But remember, the y's are actually cosecant. So I'll rewrite it as cosecant x minus 2 and cosecant x plus 1 equals 0. Set each factor to 0, and we'll try and solve each of these equations now. And now this is an equation just like you had in grade 11, a trig equation to solve. So let's move the minus 2 over. And cosecant is the reciprocal of sine, so sine would equal the reciprocal of 2, which is 1 over 2. Over here, cosecant x equals negative 1, which means sine is the reciprocal of negative 1, which is still negative 1. So I just have two equations to solve here. So sine x equals a half. Keep in mind for this one, I will get two answers. Where is sine positive? Sine is positive here and here. We can use your oh, and I should have mentioned in grade 12, you're probably solving all trig equations in radians. So what I'm going to do before I do this question, I'm actually going to change my calculator into radian mode. I think I don't actually need my calculator for this one. We can get exact answers. The special so a half, I can get that ratio from a special triangle. Remember the special triangle, the 2, 1, root 3, but I'm going to do it in radians this time. So instead of 60 degrees, I'm actually going to have pi over 3 radians. And instead of 30 degrees, pi over 6 radians. So here's my special triangle using a different unit of measure for the angle. It's in radians now. So sine of what equals a half? Well, sine's opposite over hypotenuse, so sine of pi over 6 equals a half. So I put pi over 6 on my circle, 0, pi over 2, pi, 3 pi over 2, 2 pi. So put pi over 6. Well, pi over 6 is going to be here, reference angle pi over 6. Put a pi over 6 reference angle here as well, and that will give me a second answer. So let's write these two answers. So the first answer, x1 equals pi over 6. The second answer, well, I fell pi over 6 short of going pi, so I'll have to do pi minus pi over 6. So that's 6 pi over 6 minus 1 pi over 6. That's 5 pi over 6. So two answers. Both of those, if I do sine of either of those, I should get a half. Let me just check quickly. So sine, let me check, pi over 6, it's a half. How about sine of 5, pi over 6? It's a half. Both of those work. So that would make this factor 0, which would make the whole equation be 0. What about this factor? So sine negative 1, well, it's going to be useful for the unit circle for this one. Unit circle, remember any point, so on the any point on the unit circle has radius of 1. 1, 0, 0, negative 1, negative 1, 0, and 0, 1. Any point on the unit circle, any point at all, the coordinate, the x-coordinate is going to tell you the cosine ratio, and the y-coordinate will tell you the sine ratio. So if I'm looking for an angle, so it's 0, pi over 2, pi, 3 pi over 2, 2 pi. If I'm looking for a sine ratio of negative 1, well, I'm just looking for where's the y-coordinate on the unit circle negative 1? Right here at 3 pi over 2. So I get an answer, x3 equals, x, not negative 1 or 2, x3 equals 3 pi over 2. That's another value that would make the equation 0 because it would make sine x equal to negative 1. Let me show you. So sine of 3 pi over 2, 3 pi over 2 should be negative 1. There we go. So that would be the most difficult equation you could solve in high school. If you can master solving all of these types of equations, you're going to be set for any math course you take in the future. Being able to solve for an unknown is what math is all about. Hope you enjoyed the video. Go to jensenmath.ca if you want any more material. Don't forget to subscribe.